Hi everyone, it's Mr. H here. Proving the three identities on your screen is fundamental to understand how to prove trig identities. The last one is especially important, so stay tuned for that. We'll start by going over helpful strategies, then we'll prove each identity and find the restrictions and radians for each. So let's begin by going over some helpful strategies. First, we want to simplify the most complicated side first. Second, use reciprocal identities. Memorize these. Cosecant theta equals 1 over sine, secant is 1 over cos, and cotangent is 1 over tan. Now notice that theta didn't show up for me. You'll find that if you print things using Greek letters, it'll occasionally just drop it. And so whether you're going from one program to another or printing it, just always check your work before submitting that, just to see if it dropped something by some mistake. Third, we want to get a common denominator. Fourth, look to set up differences of squares or perfect squares that will allow you to use Pythagorean identities. Let's look at some examples of this. First off, if we have sine of theta and we have plus 1, if we multiply that by sine of theta minus 1, that is a difference of squares. Now, you might not recognize this. And so what you can do if you don't recognize that is you can always let some letter equal sine, cos, or tan. So I'm going to let x equal sine theta. And so what we're going to get is we're going to get x plus 1 times x minus 1. And so now that's a difference of squares. And so that's x squared minus 1 squared, which is just minus 1. So then what we do is we can let sine theta equal x. And so this becomes sine squared theta minus 1. Now you don't have to do that. You don't have to do that with the x, but if that's helpful, that's something that you can do. Let's look at an example of a perfect square. If we had something like a sine x plus cos x, and sometimes we have an x there instead of a theta, that still represents the angle. Don't get that confused with the x coordinate of the angle. It just represents the angle still. If we have that squared, that is a perfect square. Now you might not think of how you could do that as a perfect square, so what you could do is the same method as we had before, but notice that the x being the angle, we're not going to let x be sine of x. What we're going to do here is we're going to let a be sine of x and b be cos of x. And so what we're going to get is a plus b all squared. Now we know that's equal to a squared plus 2ab plus b squared. If you had to FOIL that out and then collect the two middle like terms, you could do that, but that's something you should know by now. And so now what we can do is if we go back to let sine of x equal a and cos of x equal b, then what we get is we get sine of x all squared, so sine squared x, plus 2 sine x cos x, plus b all squared, so cos squared of x. And so that is our final result. Now you could have gone directly there. Hopefully you start recognizing that, but if you need to use the substitution method, that works just as well. Just like we could have gone directly there in that first example. So that's how we can do that and how we can set up some Pythagorean identities that we'll see in the proofs that we prove together. Number 5, when in doubt, write everything in terms of sine theta and cos theta. And number 6, keep the other side in mind. Only make changes that get you closer to the other side. Now, a lot of YouTube videos on this topic only cover the proofs, but they don't determine the restrictions. And so why am I determining restrictions as well here? Well, that's because many identities have a specific value that would not make the identity true. And so it's important that we have that restriction on those identities. And so we'll do those after each identity. Here we go. So those are the strategies, and I'll have those listed all the time when we do every proof in this video. And then you'll also notice that I have a number of identities as well. I give my students a sheet with 34 identities in grade 12 math. And so what I do is some of those identities are pertinent to this type of proving identities. And so the ones that are applicable are the ones shown here. So we'll have those shown as well as we do each identity, and we can refer to those numbers of what identity we're using as we go through those identities. So the first identity we're going to prove says prove tan theta plus cotangent theta equals secant theta times negative cosecant of negative theta. Now the first thing I want to do here is I actually want to deal with these negatives because we've got multiplying by negatives, and so if we can make things positive, that will make our life a lot easier. And so you can see what I've circled down below on identity 15, cosecant of negative theta equals negative cosecant theta. So if this was not a negative here, then we'd have negative cosecant of theta, but because it's negative of that negative, and what that becomes is it actually makes it positive. And so the right side of this equation is going to become secant theta times positive cosecant theta. We've applied identity 15 in order to get that. The left side is going to be tan theta plus cotangent theta. Now notice I've separated the two sides. I'm not trying to rearrange the equation because I don't necessarily know it's true. I'm trying to prove that it's true. So it's important we keep those two sides separate throughout the proof. Now what I'm going to do is I'm going to break down the left side further. And so the left side, I'm going to use identity number 1, that tan is going to be sine over cos. And then identity number 2 for cotangent, that's cos over sine. And you'll notice I have two fractions on the left, but when I go to the right, secant becomes 1 over cos, and cosecant is 1 over sine. And so when I multiply those together, because they're multiplied on the right, I get 1 over cos times sine. And so we have one fraction on the right, but yet two on the left. So what we want to do is we want to get a common denominator. That's step 3 in our strategies there. So in order to do that, I'm just going to write this out again. You don't have to write this out again, but I'm going to show a little bit more space here of what I'm multiplying each fraction by to get a common denominator. So what I'm doing is I need to multiply the first fraction by sine over sine, and then I'm going to get a denominator of cos times sine. I need to multiply the second fraction by cos, and then I'm going to get a denominator that's the same as the other one. So cos times sine is the same as sine times cos. The order of multiplication doesn't matter. So what this gives me on the left is sine times sine gives me sine squared theta. And the other fraction is cos times cos, which gives me cos squared theta. Because they're both over the same thing, we can write this as cos theta sine theta. And that's very similar now to the right side. And you'll notice, hopefully, that identity 3 brings that together. So if we use identity 3, sine squared theta plus cos squared theta equals 1. Now we have 1 over cos theta times sine theta, and that is equal to the right side. We have proven that identity. Now let's look at the restrictions. I've kept that proof there just so we can see that, but keep in mind that there are certain values for the angle that this won't work. And so what we want to notice is from the initial equation that we have up there, it appears that nothing's in the denominator. However, what we know from the first line of the proof there, that cos theta is in the denominator, sine theta is in the denominator, and there's cos and sine again there. And so you can see that all the way through, even at this step there and this step down there, we have cos and sine in the denominator. Now because we can't divide by 0, what that means is it means we have to look at restrictions for these. So when is sine of theta equal to 0? And when is cos of theta equal to 0? That's going to tell us the restrictions on the angle. Well, if we look at just our Cartesian plane, x and y, and if we wanted to look at some angle theta, remember theta is really in any quadrant, but let's just draw it in quadrant 1 to start here. If sine of theta was equal to 0, sine of theta is the opposite, which is y, over the hypotenuse, which is r. And so that what that means is that y over r cannot be 0. Well, r is never 0 because r is the length of the terminal arm. So that means that y cannot be 0. So we ask ourselves the question, what angle has y be 0? So I'm just going to draw this again here. And we can see that at an angle of 0, there is no y value. Also at an angle of pi, we're talking radians for this course, there is no y value. Again, at 2 pi, there is no y value, etc. So we're going to make a general conclusion here at the end, but let's work on cos now. Cos, if we draw a diagram just to look at what this looks like first here, cos is the x value over the r. And so because x over r can't be 0, that means that x cannot be 0. Well, what angle has x be 0? Well, x is 0 at an angle of pi over 2, and x is 0 at an angle of 3 pi over 2. Again, talking radians for this course. In other words, we can't have the angle be pi over 2, we can't have the angle be pi, we can't have the angle be 3 pi over 2, and we can't have the angle be 2 pi. So every pi over 2, it's not allowed to exist. And so what we can do is we can say that in general, theta cannot be pi over 2 times k. What is k? K is just an integer. So it could be 1, 2, 3, 4, 5, 6, 0. It could be -1, -2, -3. Any whole number that we put in for k, any integer value for k, it's going to make the x value 0 or the y value 0. And so what we're just going to write here is that k is an integer. Just a bolded I to say that k is an integer. So in general, theta cannot be pi over 2 times some integer. That is our restriction for that first proof. Number 2 says prove cosine beta over 1 plus sine beta equals 1 minus sine beta over cos beta, and list restrictions. So let's go ahead and separate the left side and the right side. So the left side is cosine of beta over 1 plus sine beta. And the right side is equal to 1 minus sine beta over cosine of beta. Now you'll notice here that because we have two terms in the denominator of the first fraction and one in the second, we somehow have to get those to be the same. There's nothing that relates 1 plus sine to cos unless things are squared. And so that should be our hint that we should look to do a difference of squares or a perfect square. So the temptation might be to change both sides at the same time, but let's change one at a time and try to get it to look like the other side. Don't change them both at the same time. So what I'm going to do is I'm going to multiply the left side by 1 minus sine beta over 1 minus sine beta. And so I'm going to make sure I have brackets there so that I'm using that difference of squares properly. And so this becomes cosine of beta times 1 minus sine beta. I'm keeping that like that for now. I'm not going to expand it out yet because I'm interested in this 1 minus sine squared beta on the bottom. That's a difference of squares, the first term squared minus the last term squared. And so what we get is something that we can rearrange here actually, because this is very similar to identity number 3. And so because identity number 3 says sine squared of an angle, beta in this case, plus cos squared of an angle, beta, equals 1, if I rearrange that for cos squared beta, what I get is I get 1 minus sine squared beta. And so I can rewrite this as cos of beta times 1 minus sine beta on the numerator divided by cos squared beta. And very nicely, that cos of beta on the top cancels out with one of the two on the bottom, leaving me with 1 minus sine of beta over cos of beta. And that is proven that the left side is equal to the right side. Let's now look at restrictions. Now the first thing to note is that 1 plus sine beta cannot be 0. We brought this 1 minus sine beta in as part of the proof, but that isn't necessarily a restriction. But what is what's written in that first line. And so what we're going to do is we're going to say 1 plus sine beta cannot be equal to 0, which means that sine of beta cannot be equal to -1. And so because sine, as we said before in example 1, is y over r, that can't be equal to -1, that means that y cannot be equal to negative of r. Well, when is y equal to negative r? Well, r is always positive, so it's the only case where y is negative and where it's the same length as r. That's the situation where we are at 3 pi over 2, all the way around like so. And so that sets a restriction at 3 pi over 2. The other place we have a restriction is cosine of beta. Now cosine of beta, that can't be 0. And so what cosine we know is x over r, so that means x over r can't be 0, which means x can't be 0. And so if I was to draw where those restrictions are, this is actually the same as we saw in the first example, where x is 0 at pi over 2, and x is 0 at 3 pi over 2. And so we get the same restriction from cos as we do from the sine beta cannot be equal to -1. And then we also have the restriction that pi over 2 is not allowed. Now, in this case, as is different from the first example, we don't have a restriction at pi and 0 and 2 pi. And so that we need to account for. So what we're going to do here is we're going to say in general that the restriction is that beta cannot be equal to pi over 2, And then how much do I add to get to 3 pi over 2? Well, I add pi. But then I add pi again, and I get back to pi over 2, but after having gone past one rotation. And so we're going to write that as k times pi, where k is an integer. So k could be 1, 2, 3, 4, 5, 6. It could be 0, -1, -2, -3. All that pi times k does is it just brings me another half rotation around back to the next part where we have that restriction. And so there is our restriction on that trig identity. Those are the angles when that identity does not work. But for any other angle, that identity works. So on to example 3. The left side is sine x minus cos x over sine x plus cos x. And the right side is 2 sine squared x minus 1 all over 1 plus sine of 2x. Now notice here that the x is representing an angle. Sometimes we have an x or a y that represents an angle, but it never represents the x or y coordinate if it's following after the sine, cos, or tan, etc. And so the first thing I want to do now that I've established that is I want to recognize that this sine has a 2x that it's operating on. It's not an x. And so we want to get those to be the same. And you can see I've already circled the double angle identity below. Sine of 2 theta, in this case it's x in place of the theta, is equal to 2 sine theta cos theta. So what I'm going to do is I'm going to write this as 2 sine squared x minus 1. And this is going to be written as 1 plus 2 sine x cos x. And so now that I have everything written as the same x's for the angles, I can go ahead and now work on the left side. What I want to do here is I want to recognize that these are different signs, and I can't combine sine and cosine unless things are squared. So what I want to do is I want to multiply this by, you could either multiply by sine x plus cos x on the numerator and denominator, or by sine x minus cos x on the numerator and denominator. You'll work it out either way you do this. And it's important to keep in mind there's many ways for proofs to get to the final answer. What I'm going to do here is I'm going to work with adding those. So sine x plus cos x. And then on the denominator, I'm going to have the same thing to keep that fraction the same. And so what's going to happen is the numerator is a difference of squares. So we get sine squared x minus cos squared x. And then on the denominator, that is a perfect square. And so what we're going to get is sine squared x plus 2 times the first term times the last term plus cos squared x. At the beginning of this video, I showed you how you could use substitution to do that. You could do that if you want, but if you're comfortable with this, as you should start getting comfortable with, then this is a quicker way to do that without having to use substitution there. So remember, the identity that we're going to use here is sine squared x plus cos squared x is equal to 1. And that is not to say that if it's a minus between them, it's equal to -1. That's totally not true. So what I'm going to do for the numerator on the left is I'm going to start by letting cos squared x, that's equal to 1 minus sine squared x. So I'm going to replace the cos squared x with that. So I'm going to have sine squared x minus 1 minus sine squared x all over. And the denominator, I'm going to recognize that I have a sine squared x and a cos squared x. That gives me 1. So I'm going to get 1 plus 2 sine x times cos of x. And now we're actually very close to what the right side is. And so the sine x, I'm going to just expand this out so you can see this. The sine squared x minus 1 plus sine squared x, because that negative gets expanded in the bracket and changes the signs of everything in the brackets that follows, divided by 1 plus 2 sine x times cos x, and the sine squared x and the sine squared x combined together to give me 2 sine squared x minus 1 all over 1 plus 2 sine x cos x. And that is the same as the right side. So the left side is equal to the right side. We've proven the identity, but we still have to list the restrictions. So this one's a little bit unique in that we have a sine x plus cos x there, and we have a 1 plus 2 sine x in the denominator on the right. Let's deal first with the sine x and cos x. So these cannot be equal to 0. So what that means is that sine x cannot be equal to negative cos of x. Well, let's think about when that's the case. Sine x is y over r. And cos of x is x over r. So it can't be equal to negative of that. So it's negative x over r. In other words, y cannot be equal to negative of x. So if we go ahead and we draw our Cartesian plane, there's our x-axis and our y-axis. When is y going to be equal to x first? Well, y and x are the same when we have an angle there of pi over 4. The y value is equal to the x value. But that's not the situation that we care about here. We care when it's negative. So when else are the magnitudes the same? Well, the magnitudes are also the same when the y value here is equal to the x value. But here this would be a negative x value. And so this is a related acute angle of pi over 4, which means that the principal angle going all the way around is actually going to be 3 pi over 4. And so that's the first restriction that we have. If we continue that down into the third quadrant, where we have the x and y magnitudes to be the same, the y value is negative and the x value is negative, so they're not negative of each other. And if we go to the fourth quadrant now, and we say, well, the y would be negative, the x would be positive, they would be negative of each other there again. So that related acute angle of pi over 4 in that fourth quadrant gives me a principal angle of 7 pi over 4. And so 7 pi over 4 and 3 pi over 4 are going to give me my restrictions for that. But what about the 1 plus sine of 2x? That can't be 0. That's from the right side. And so what that means is that sine of 2x cannot be equal to negative 1. Well, when is sine of x equal to negative 1? Well, I'm going to think about sine of x and then we'll deal with the 2x here in a moment. Sine is y over r. That can't be equal to negative 1. Well, when is that going to be the case? Well, y over r, that would be when y is equal to negative r, which is going to happen when we are at 3 pi over 2. We've discussed that in the first example. We saw that come up as well. So that would be when we have a principal angle of 3 pi over 2. So what that means is that 2x, because remember that angle is 2x, cannot be 3 pi over 2. And if we solve that for x, that means the restriction on x, if we divide both sides by 2, gives me 3 pi over 4. That's less than half of a circle. And so anytime you have a number in front of the x, you have to go around your entire circle that many times to get all the restrictions between 0 and 2 pi. So what I'm going to do here is I'm going to go ahead and I'm going to go for 2x cannot be equal to, if I went all the way around the circle again and back here again, what I'd have 7 pi over 2. 2 pi more than 3 pi over 2. And so if I divide both sides by 2 again, that gives me x equals 7 pi over 4. And you can see that's also an angle that is between 0 and 2 pi. And so that's why we have to go around twice, because that 2 is in front of the x. So we have the same restriction on both the denominator on the left and the denominator on the right. And so now we can write our general conclusion. And so that means that x cannot be equal to 3 pi over 4. And then what we're doing to get 7 pi over 4 is we're adding pi. And then if we want to get the next go around to the same thing as 3 pi over 4 was, we'd add pi again to get that. And so we're going to go plus k times pi, where k is an integer. And so we started at 3 pi over 4. That's what that means. And then if we added k being 1 as an integer, then we got to 7 pi over 4. And if we added k being 2, then we kept going around back into quadrant 2 again. If we added 3, we're back to quadrant 4, etc. And so that's why k is any integer. We could also rotate the other way, and those could be negative values, and it would also get us into quadrant 2 and quadrant 4 for those same related angles in those quadrants. If this video was helpful, I encourage you to like and subscribe. Please check out the videos above for more on trig identities, and thanks so much for watching.